So today's presentation is about our machine learning project for 5012 in Hong Kong USD. And the objective of our project is classify image classification of fish species. The content of the presentation is divided in 4 steps. First, we'll talk about the overview of our project. Second, we will discuss about the methodology we follow. Third, about the experimental results. And finally, we'll show a demo. So for the overview, as I mentioned before, in our project, our objective is to design an image classification model that will classify fish species. The dataset of the project is related to fish species, and whenever in Hong Kong or in other countries, when we visit local markets and we try to buy some food ingredients, sometimes it's hard or challenging for us to identify some of the fish species. Probably the easiest one, like salmon, it's not hard for us, but maybe there are other species that we require some help, and maybe we need to check the label before knowing what we are buying. So with our model, we'll try to help people have easier access and easy understanding of what they are buying, and to know more about different families of fish species. All the project at the start, we try to implement it using Jupyter Notebook in our own local machines, but finally we decided to use Google Colab and PyTorch based on all the potential they can provide. So second, for the methodology, basically we have our data set, we pre-processed this data, and then we created our model. So the dataset, finding fish image is not easy. Not so many people or companies provide that information. So we found a dataset with around 70 or more than 70 different types of species for fishes, but we reduced it only to 23 species because the number of samples, or let's say image, for some of these species was quite low. For that reason, we reduced it to 23 species. We have around 2,500 total of image, and then we divide it between a training set, validation set, and testing set, trying to follow the structure of 75% for training, 15% for validation, and the rest for testing. And also we can see more or less the number of image for each one of these subsets of the data. Here is a visualization with the total distribution of image for each one of our species, 23 species of fishes, and we can see in blue the training data for each one of the species, in red the validation data, and finally in yellow for the testing data. As we can see, in average, most of the species have around 30 to 40 image that we could use for training, testing, and validating, but also we can see the image here in the center, they have more than 100, 200. So probably our model will have an easier task to learn from them, and also easy for them to classify. Maybe for classes like this one, maybe the model will have more problems because we don't have that much information to train the model. So once we have the data, once we found which data we want, once we more or less clean and reduce the number of samples in our data and the number of classes in our data, then we need to think how we can input that information or this image in the model. First of all, we could think we can grab directly the raw information we have, the raw image, and directly input in the model. But because the data includes not only pictures of the fishes, some of the fish pictures could be cropped, so the noise behind the actual fish is removed, or also some of these pictures are actually drawings of the fish we want to classify. This can create some noise if we input it directly raw in the model. So we need to do pre-processing. How we do pre-processing? First of all, we resize all the image so they have this similar structure. So here we resize to 256 pixels. Second, we crop the image. We input directly the image to the model. We are not generalizing, so when a new image arrives, depends on the rotation, depends on the amplitude of the image depends on the quality of the image, the model won't be able to predict correctly. So in order to do so, that's why we are doing cropping. We are adding some, for example, some brightness, some contrast, some saturation. We are transforming to grayscale, and we are applying other pre-processing steps to try to generalize all the information we have. And here it will be an example of after we preprocess our image, it will be the final output that we will introduce in the model for the training, validation, and testing. As we can see here in the left side, the top left image, we see that the image was rotated. We also see the image was cropped, and this actually is showing for 4 different species actually the most important feature that is gonna be input in the model and train. What model? We extracted the data, we pre-processed the data, and now we need to define the model. So for the model, one of the techniques you can use is actually transfer learning. So transfer learning basically is someone, a company, a team, a group of people develop a model for one specific objective. In this case, it's image classification. And transfer learning, what it does is use the same structure of the model and the same way it's learned before to retrain that model with your new data and to adapt that model to the new objective, in our case, fish classification model. Why we choose this model? First of all, in 2015, won one of the ImageNet challenge, and the error was quite good compared to other models. Also, in PyTorch, in the right table, we can see a list of different models they provide and how good they are in comparison to the others. So in our case, we chose this one, but for future studies, we could try to do transfer learning with more than one and actually compare how good they are one versus the other. We tried ResNet 18 versus ResNet 152, and we decided to follow with the ResNet 152 because it gave us better results. So for the model settings, we needed to specify a loss function. We needed to specify also the optimization and also for regularization. For the learning rate, we tried different combinations of learning rate, but at the end, the one that worked the best is learning rate with 0.0005. And also we add a decay on the learning rate. Decay means every X amount of steps, in this case, X amount of epochs, 7 epochs, the learning rate will be decreased by a factor of 0.1. This is going to help the model improve the accuracy and improve the training, so our prediction should be better. For the experimental results, for fish classification model, the accuracy at the end, after training the model, doing the validation and testing with our data, is around 80%. And on the right graph, we can see the evolution of the epochs and the accuracy for the training and for the validation. So basically, we can see in the last epochs from 18 to 20, the system starts to stabilize. So there's not such an increase of accuracy. So we stop in epoch 20 because it gave our best results. We tried different things to improve our fish classification model, but they weren't successful. One of our beliefs is because the data. First of all, the data is quite hard to work with because, as I mentioned before, we have actual image, we have drawings. Second, we don't have so many samples for each type of species. And third is a problem also related to the amount of information we have in the models. We don't have that much information to train, and this is giving us problems in the accuracy. So what we try to do, we got another data set and we used the same model to train a flower classification model. So with a better quality on the data set, the model accuracy also improved. So for classifying different types of flower, we got nearly 92% accuracy. So that's one of the reasons we believe our model wasn't as good as we expected, because the complexity of the data used. During the model training and comparing the results, we try to use different inputs in the model. One was the learning rate. We try to modify the learning rate and see how this will affect not only the fish data set, but also the flowers data set. If we compare the values, we see that the best learning rate is the one that I mentioned before, 0.0005, and that gave us the best accuracy for both data sets, not only for the fish, but also for the flowers. Actually, reducing the learning rate, it only helped on the fish data set. So that means maybe it's give us an idea that the prime also is in the data set. Second, we try to use different optimizers. We try to use HGD optimizer, and also we try to use Adam. And if we compare in the tables, the best one was HGD. With HGD, we achieved nearly the 80% accuracy. With Adam, we got really, really low accuracy for both datasets, flower and fish. Visualization, basically on the top left corner, we can see the confusion matrix. And on the y-axis, we have the real classes, and on the x-axis, we have the predicted classes. So here we can identify different clusters, for example, in this one, or for example, this one, where between two classes, there are some mismatchings on the predictions. And here will be an example how two different types of species of fishes actually have some similar attributes that can make the model predict wrongly. For example, Lujanus species has more than 15 subfamilies inside. And as we can see, each one of these subfamilies looks quite different from another. Also, what I mentioned before, we have real image already cropped with no noise, some image with noise, and also we have some drawings. So if we have few samples for one of the subfamilies, the model will have hard times to predict into the right family. So at the end, as a summary, if we have high variation between subfamilies and we have few samples of each one of the subfamilies, the model will have a hard time to improve the accuracy because it won't be able to predict correctly and there will be mispredictions. So for the demos, when we input a new image in the model, in order to predict, basically the output of the model, here we can see that will be our input, will be Epinephelus, and the output of our model will give us like the different classes the model predicted, or the different species, and also the confidence level. And in this case, it predicted correctly it's an Epinephelus with a 97% confidence, but also could believe it's another species, but only 2%. 2% is so low, so this one will be discarded. Thank you so much. And in the future, we would like to try improving the data set, and we believe improving the data set will improve the accuracy of the model. Thanks.